Let's look to one more problem. So the problem is following. We have two numbers, A and B, and want to find how many primes between A and B. We already discussed how to check for some number, for some integer, is it prime or not in previous video. Please look it if you don't know how to do it. And assume that we have 1 second time limit, and for A and B, the borders just 2 from, it can be just numbers from 2 to the 10 to the 4. Okay, how we can do it? So firstly, using the idea from the previous video, we can just check all numbers from A to B. And if numbers that we are checking, number P is prime, then we just increase counter. But if it is not prime, then we do nothing. Okay. And also we can add this break, and it's improve our running time, because there are many not prime numbers in some segment. Here, this improvement can be really helpful. But so one way how to improve our code from the beauty point of view, we can put it as some function is prime. But what about time complexity? So we know that this time function is prime work with time complexity square root of p. And in the case of running this function with p from a to b, we have complexity. First running takes square root of a, then square root of a plus 1, then square root of a plus 2, and so on, square root of b. We can say that each summat in this sum is at most b, square root of b. Then we can say that it's square root of b times number of elements in this sum, that this is b minus a elements plus 1, in fact, but we don't care about these constants. So this is b minus a times square root of b. Also, we can say that b is a is at least 2, then the total complexity is b square root of b. So if here b is at most 10 to the 4, then it is 10 to the 6 operations. It is about 10 milliseconds. For our time limit, that is 1 second. It is very good. But at the same time, you can see that if b and a very big, but b minus a still very small, for example, numbers, our segment is just 10, yeah, and b is 1 million, then it is like primes from million to million 10, then it is still very fast, because b minus a can be 10, and square root of b is just 1000, and it is 10 to the 4 operations. It's very fast. Yeah, but if we just multiply million times square root of million, then it is 10 to the 9, and it is longer than 1 second. So that's why sometimes this formula is also very useful. So, but if b is up to 10 to the 7, then the number of operations is 10 to the 10, and it is more than 1 minute, and it is not acceptable for us. We should improve something. We can use new idea. Let's have Boolean array that of size of the size is b, it is 10 to the 7 in that case. And for each this Boolean array mark as for each number, is it prime or not? For example, if we look to the number I, the ith element of our array is true if I is prime and false if I is not prime. It is somehow we can say that this is indicators for each number, is it prime or not, or it somehow represents a set of prime numbers in our segment from A to B. So here from not from A to B, from 2 to B, because we care about all numbers up to B. So at the same time, if some number P is prime, then we can say that all numbers that are multiple of P are not prime. So any number J such that J is P times some integer K is not prime. And if we look to any prime number P, we can assign false for all elements with indexes P times some integer number, where K is more than 2 or bigger. So this is our idea. We check all numbers from 2 to B, and if we look to this number, and if it is prime, we will mark all not prime numbers that are bigger than this one. So if some number P is prime, then we can, if it is true, we can be sure that it is not divisible by any prime number before P, because for any prime number before that, we already run this process. We mark all elements that are multiple of these numbers, and that's why if we have true for some element with index P, then it means that it is not multiple of any primes before that, and this process that we done for each primes before doesn't mark it as a false. That's why we can be sure that P is prime, and we can run the same process marking all elements that are multiple of P by false too. So we obtain such a code. Firstly, we think that all numbers may be prime and mark them as a true. But after that, we look to each number. If it is true, then we go. So firstly, we find the prime number, we count it, and after that, we go by each number from each multiple of P. So J is 2 times P, then 3 times P, 4 times P. We do it using the J plus equal P. Yeah, this operator, and to mark by false all these numbers. So in fact, the just counting numbers that are prime is not correct, because we should count number of primes between A and P. That's why we check if P grades A. In that case, we count our counter. So let's check, is it fast or not? What is the time complexity of such a code? So definitely the first four takes B steps. Then if we look to this part, this inner four, first it takes B over 2 steps, then B over 3 steps, then B over 5 steps, and so on. So we, by prime numbers, we have such a sum. We should estimate them, this sum. So first we can say that this is just constant, and each summate is atmos B, and there are B summates here atmos. That's why the sum is B squared. But it is the same running time as for the idea that use checking each number for is it prime or not. But let us estimate it more carefully. Let's look to this sum, and we can say that B would be out of brackets, and we have such a sum. And we can say that yes, here only prime numbers, but we can add summats with our numbers. It is easier to estimate this sum, and we know that this sum is the just harmonic series, and its sum is just log B. That's why this B log B. So B log B for B is 2 to the 7, just 10 to the 8 operations. In fact, this sum, if we put only prime numbers, it is B log B, but hidden constant is very big. That's why B log B is better time complexity for estimation. Okay, and the total ID, total algorithm called Sieve of Eratosthenes. So we can use it for our problem. In these 3 videos, this video and previous 2 videos, we understand how to estimate running time, how to improve running time by some additional ideas, and we see that sometimes careful estimation of running time is very important because sometimes you have good solution and maybe you can think that it's not very good, but in fact, if you estimate running time complexity very carefully, you understand that it is really good solution, and also a little bit discuss memory complexity and beauty of form. Also, we remember some facts from math analysis and understand that it is important to use it and apply when we estimate running time, and it can help. Thank you. See you in the next video.